All right, let's just jump right in. Have you ever thought that maybe there are these hidden codes, like buried deep inside mathematics itself? I'm not talking about just problems to solve. I mean a fundamental language, an architecture that maybe, just maybe, governs everything. Well, today we're going to explore a really fascinating and seriously complex theory that says, yeah, that's exactly what's going on.
It all kicks off with this number right here, 65537. Now, at first glance, it probably doesn't look like much, right? But this number is a quiet giant. It's an absolutely crucial piece of the digital world that we all live in. So what on earth does it do?
The answer to that question, well, that's our first step on a pretty wild journey into what some theorists are calling a hidden architecture of numbers. We're talking about a system of resonance, of rhythm, and rules that connects prime numbers, infinite sequences, and maybe even the very fabric of physics itself.
So what is the big deal with 65537? See, it's not just any old prime number. It belongs to a really rare family of primes called Fermat primes, and it's basically the anchor for the RSA algorithm. And if you don't know what that is, it's the encryption method that protects pretty much everything you do online. Your banking, your emails, all of it.
The reason everyone chooses it comes down to its beautiful, elegant binary structure. Get this. It's just a 1 followed by 15 zeros and then another 1. For a computer, that super simple form is incredibly easy to work with, which makes all the complex calculations needed for encryption happen at lightning speed.
So it's this perfect trade-off, right? When a computer uses 65537, it only has to do 2 multiplications and 16 squarings to get the job done. I mean, that is ridiculously efficient. And it means our online transactions are super fast, but the number itself is still beefy enough to be incredibly secure. It really is our stable anchor, kind of like the master key, this perfect oscillator humming away in the digital world.
Okay, so 65,537 is our anchor. Got it. But how in the world does it connect to everything else? To get that, we've got to zoom way out and look at the huge system it's a part of. Just imagine for a second that we could create a geometric map, like a highway system, for all the numbers that exist.
And that's the core idea of what's called the 36 modular system. Think of it like this. You take the infinite line of numbers, and you wrap it around a 36-hour clock. When you do that, something really amazing starts to happen, especially with prime numbers. A hidden pattern, a kind of rhythm, just starts to pop out of the chaos. And this is where that pattern really shows up. According to this theory, every single prime number bigger than 3 has to fall into one of these 12 specific lanes on our 36-step clock. It's incredible. This creates a predictable highway system just for primes, and it lets us immediately rule out 2/3 of all numbers when we're searching for them.
So what this framework really does is transform number theory from just a static list of facts into a dynamic, moving system. Every number suddenly has an address and even a directional spin, which tells you how it rotates through the cycle when you're doing calculations. It's literally like a GPS for finding primes and predicting how they'll behave.
Okay, so we've got an anchor and we've got a map. But every system needs a pulse, right? A heartbeat that drives its rhythm. And the next piece of this puzzle, well, it comes from a number you would never, ever expect.
-24. I know, it seems totally out of place, doesn't it? But according to this theory, this number is the system's stabilizing anchor. It's a residue that marks the symmetry axis. It's the balancing point of the entire 36 modular system. So where does a weird number like that even come from? Believe it or not, it comes from the famous Fibonacci sequence. So if you take every number in that infinite sequence and you boil it down to its digital root, you just keep adding the digits till you get a single number, something incredible happens. All the chaos just vanishes, and this perfect repeating cycle appears. And guess how long that cycle is? You guessed it, exactly 24 steps. This is the system's heartbeat. And you know what? This 24-step cycle, it echoes one of the absolute weirdest, most mind-bending results in all of math, the Ramanujan summation. It's this famous, kind of crazy formula that's super important in string theory. It basically says if you add up all the positive integers, 1 plus 2 plus 3 and so on, forever, you somehow get -1/12. I know, it makes no sense, but this theory, it argues that our heartbeat number, 24, and this cosmic number are basically two sides of the same coin. They're the bridge between the finite math we use every day and the wild physics of the infinite. So we have our anchor, the map, and the pulse. Now we just need a filter.
something to help us refine the map and bring this whole picture into sharper focus. And for that, we turn to a clue from the history of mathematics itself.
This specific chain of numbers, which comes from the work of the pioneering mathematician Sophie Germain, acts as our filter. You can think of it as a set of coordinates. According to the theory, these numbers pinpoint key intersections and nodes along our prime number highway, really helping us navigate the system.
You see, Sophie Germain studied this really special class of prime numbers, where a prime p could be used to generate another prime using the formula 2p plus 1. These special primes act as our sieve, and what's remarkable is that they create a direct causal link to another famous family of primes, the Mersenne primes.
And this connection isn't just a coincidence. The theory says it's a fundamental rule. So if you take a Sophie Germain prime like 11, its partner, 23, has to be a factor of a corresponding Mersenne number. It's just a rule. This shows a deep, predictable, and causal link between families of prime numbers that we used to think were totally separate.
So here we are. We've got our four components: an anchor, a map, a pulse, and a filter. Now it's time to put them all together into a single unified theory, the Universal Resonance Code.
Here they are, our four core components, all working together in harmony. The stable anchor, 65537, gives us that cryptographic frequency. The 36 modular map gives us the geometric space. The -24 pulse provides the rhythm. And the Sophie Germain chain gives us the logic to filter it all. It's a whole system.
So what's the real-world application of all this? Well, this unified theory points to a brand new type of cryptography, a knapsack RSA hybrid. Basically, it combines two famously difficult math problems into a single layered system that is, at least in theory, way more robust and secure than the methods we use today.
The big overarching name for this whole framework is the Gadou-Assa paradigm. And it's a pretty radical idea. It's asking us to see numbers in a completely new light, not as static, fixed values, but as active elements, like shadows or projections of deeper dynamic functions that are all resonating together.
And this is basically the Rosetta Stone of the entire theory. It's like a periodic table, where each key number we've talked about is given a dynamic identity and a specific job to do. You've got 65537 as the oscillator, -24 is the anchor, the Mersenne primes are termination points. Every single piece has a purpose in this grand mathematical machine. I think this quote from the source material really just nails the whole vision of this framework. It's not just a collection of weird mathematical oddities. It's a symphony where every single element, every number, is playing a precise role to maintain a universal mathematical balance. Which, of course, leaves us with one last massive question. Is all of this just a clever model that we invented? Or are we, maybe, finally beginning to decode a fundamental language that's woven into the very fabric of reality itself? A language that's just been waiting for us to figure out how to listen.